Okay, ladies and gentlemen, now let me know or let me let you know what's happening. Today is Friday, February 9th, and this is 6-1 Law of Sines. Just a reminder that we are having a review day again on Monday. Tuesday is part one of the test. Wednesday is part two of the test. And I also gave out the homework sheet for chapter 6. It either is on my YOLA site or will be by the end of the day. And this is law of sines, one of my favorite things to do in the whole world. So in the world of trigonometry, yes. So we're going to use the law of sines to solve oblique triangles. And oblique triangles are simply triangles that are non-right triangles. And right, we're going to use angle, angle, side, or angle, side, angle, and then there's the naughty word backwards. So this one is the one that's going to give us a little trouble, and so, I'll just even write the word trouble there, because as you know from geometry, if you have in geometry two triangles where two pairs of angles are the same and any pair of sides are the same, then those triangles have to be congruent. So likewise, if you happen to have one triangle where you know two angles and a side, it has to be a unique triangle. There has to only be one triangle like that. However, when we have side-side angle, and just kind of a little reminder of that, where we know this angle and we know the length of this side, I'll just call it A, and the other side that we know is this side right here. Well, a lot of things can happen with that side. It can it can be it can be a swing angle, and I don't know that I can swing it there. Um, I Yeah, but I wanted it to be and then slide it. Yeah, I wanted it to be like just a little stick there. So it might make another triangle by being turned like that. It could even be that when we have that, let's see, that other side. So here's the angle, and it's these two sides, the green side and that red side. It could be that it doesn't make a triangle at all. That it just sort of hangs there from that vertex at A and doesn't make a triangle at all. It could make a right triangle. And so a lot of things can happen with that particular situation. But when we have two angles on a side, it's always going to work out. Then we'll just find the areas. That's just a formula thing. And then use the law of sines to model and solve, of course, real life problems, as we often do. So today we're just going to have that introduction for the law of sines. And the beauty of this is that now when we move away from right triangles, we can still find things that are related to that. And so this is for triangles that have no right angles, and so we call those oblique triangles. And you'll notice on that picture that just a little reminder that capital A, which is angle A, is opposite lowercase a, which is the side. And so that's a standardized notation. You've used that, way since the Pythagorean theorem is kind of what comes to mind. And so to solve an oblique triangle, we have to know at least one side and two other measures. So that is a basic information. Sometimes when we're using the law of sines, what we need to know, what we can have given to us, is different than when we know the law or use the law of cosines. And right now, I'm going to tell you that for using the law of sines, we have to know at a minimum, know or be able to find, that's how I have to say that, know or be able to find an angle and its opposite side. We have to have a pair of those. So instead of being told little a and angle A, if I'm told those two angles, then then I can find angle A. So they don't necessarily have to tell me angle A, but I have to have a way of finding angle A if I know that little side A as my only other side as I go. So here are the four cases that we can have, and the first two use the law of sines, and the next two use the law of cosines. So if we have two angles and a side, so angle, angle, side, or angle, side, angle, doesn't matter what two angles and what side. And think about why that is, because you can always find the third side of a triangle, because they always add up to 180. Then two sides and the angle opposite one of them. I have the little star there just because that reminds us that's the one that can give us a little bit of trouble. And then when we know three sides or side angle side, two sides and their included angle, then we'll use the law of cosines. So this section is on the law of sines in particular. And so here is the law of sines. And I'm just going to remind you, truly, you can put the side over the sine of the opposite angle, or you can put the sine of the opposite angle over the side. As long as you're consistent, it really doesn't matter at all. So if ABC is a triangle with sides little a, little b, little c, then little a over sine capital A equals little b over sine capital B equals little c over sine capital C. And of course, it can be written the other way as well. And that is definitely something you want to commit to memory. It's not going to be hard to remember probably. So I'll give you a moment or two to write that, and then we'll look at some problems. We'll start with problems that are going to work easily. I don't know if you want to draw the pictures, you can. If you don't want to, you don't have to. We'll draw pictures kind of like that when we get to that kind of problem where we have to be careful of that swinging back and forth leg as we look at things. But it's up to you whether you draw triangles for this one, I would say. Okay, so here's our first problem, and maybe just take a moment or two. First, just identify the fact that you cannot use the Pythagorean theorem and SOHCAHTOA here because you've got a 102-degree angle, so immediately you know that this is not going to be a right triangle. So this is the section called law of sines, and we haven't had the section called law of cosines yet. So, we know that's what we're going to use. But when we get down the road to the testing part of all of this, you want to know an easy way to identify for yourself whether you're going to use the law of sines or the law of cosines. And so the big indicator is if you can find an angle and a side that are opposite each other where you either know or can figure out easily both of them, then you're going to use the law of sines. So when I look at this, I see that I have this length of this side and I have this opposite angle here. And so that tells me this is ready to go for a law of sines problem. And so you want to find that pair. And keep in mind, when I have two angles, even if I had had side A as a known thing, I could find angle A, correct? So it would still be the same situation. So the first thing I would do is find capital A. And I think when I did one of those, we were using kind of 90 minus x. So now we do have to go 180 minus 102 plus 29. And so A is equal to, let's see, 180 minus 131. So A is equal to what? 49. So A is 49 degrees as we look at that. And so that just gives us one more thing. This is the point at which, it's most desirable if we can use the given information to find answers because, pretend I made an arithmetic error here with my 49. Do you know what I mean? As soon as I start using my 49, then if it was wrong, and then I'm going to be in trouble. But also, I will say that's why I ask that you show work, because if I know you picked to use that 49 at some point, then and you had it as, I don't know, 39 or something, then I'll know whether you're following the same correct procedures. And having said that, I'm just going to say bottom line is sometimes you have to use an answer to find the next answer, and it's unavoidable. So just kind of keeping that in mind. So this is my pair of things that I know that are opposite each other. I can choose to use that one, and I can find either A or C as my next thing. Since C was the given one, I'll just find that little c as well. And so I'm going to write 28 over the sine of 29. 28 over the sine of 29 degrees equals, and then I'm going to find little c over the sine of 102 degrees. Also, whenever possible, we want to just do one big typing problem and just be done with it. Am I okay with cross multiplying, correct? And so C is going to equal 28 sine 102 degrees divided by sine 29 degrees. C is approximately, and I don't know that it told us to round. So if it doesn't tell you to round, as long as you round appropriately, that's the most important thing. So does anybody know what that is yet? I rounded it, it looks like, to 2 decimal places. Anybody have something? Yep. And when I wrote it, I just wrote 56.49. Notice it is in feet, and I will tell you right now that I do expect you to label if there's something given. And same with the degrees, I want you to label that as well. So once I have that pair of things that matches, then I just kind of can keep using that 28 over the sine 29 degrees. And in this case, I am going to use that 49 degrees, especially that arithmetic problem. I'm pretty confident in that. And so it's going to equal A over sine 49 degrees. So A is equal to 28 sine 49 degrees over sine 29 degrees. And I forget on the little calculators, can you scroll back? Does it have that kind of scrolling back feature? So if you can scroll back, like, just you can change the 102 to a 49, and then it's gonna work out for you as well. So see what you get for A. And what did you get A approximately? Anybody get it? 9. Uh, A is approximately 43.59 feet. And so they don't ask you to draw a lot of pictures. I will tell you that by the end, you'll have to be able to draw these pictures as you go. And so here's our next one. And I love this next problem because I've seen this pole. Um, well, it's a telephone pole. So, um, so here's the thing you have to be careful of. So if you had this in one of my geometry classes, that pole would be perpendicular to the ground, and we would say it was perpendicular and everything else. But have you ever seen a pole that's not perpendicular? Yeah, we've all seen those. And so that's what we're, fine tuning our skills for. So this is a pole that tilts towards the sun. And it's kind of ironic that it says towards the sun, because like if it were a living thing, you know what I mean, it might. But this is just to give that towards the sun because it's giving you that sundial angle, is why it says that. It always just seems a little unique to me. And so it's tilted towards the sun at an angle of 8-degree angle from vertical, and it casts a 22-foot shadow. The angle of elevation from the tip of the shadow to the top of the pole is 43, excuse me, degrees. How tall is the pole? So, the book authors drew this picture, so I've left it here for you. But there's our pole tilting 7 or 8 degrees, wow, from vertical. And so this is a 98-degree angle. So obviously not right. And we are 22 feet away is that shadow that we're getting. And then this angle of elevation is 43 degrees. And our job is to find kind of A. And so I'm just going to draw it again. So I know this is 98 degrees. This is 22 feet. This is 43 degrees. And this is A that I'm trying to find. Capital A, B, C, little b is there. So in this case, and again, I know one side, and I don't know if you paid attention, but if I know one side, it's going to be law of sines. And so this is the side that I have. And I need the side or the angle opposite it. I don't directly have it, but do you agree I can find it, correct? So I need to figure out that angle to have that matching pair. So capital C, even though it doesn't ask me, I need 180 minus 98 plus 43. What's C equal to? 39. So C is 39 degrees. Now, that's the angle and side pair that I have to have. And again, it doesn't matter whether I put the side over the sine of the opposite angle or I go the other way. So I'll start 22 over sine 39 degrees equals, and my goal was to find the height of my pole. So that's this side A, and the angle opposite that is the 43-degree angle. So A over sine 43 degrees. When I cross multiply, I'm going to get A equals the two that I know, both of them, multiplied 22 sine 43 degrees divided by sine 39 degrees. And again, I'm giving this one to the nearest hundredth, 2 decimal places as well. So, who has an answer for this one? What is it? Oh, no, it is not. Okay, um, 23.84 feet is that one there. So, the next thing I have for you is two problems. For the people who are in the room, I gave them a half sheet of paper. They're going to do these, and actually, I'm going to pause the recording. I think if I do that right, I pushed that one right. Okay, so I'm going to pause the recording, and then when I come back on, we'll go over it. So it shouldn't be a long pause for those of you who are watching this. So I'm pausing this. On number 1, you're finding the remaining sides and angles, and in number 2, you're finding the height of the tree. So we'll pause that and let you figure that out. Okay, so everybody's had a chance to do these two problems, and I've collected their papers. And so now I'll just show you what the answers are right now, and then I'll look at them and we'll maybe look at it a little bit more next time as we go. So now we're going to start looking at the ambiguous case, and for the ambiguous case today, we're going to write the possible situations, and then we'll kind of delve into that after we get our next test done. So this is called the ambiguous case, and it's, you know, in geometry we called that the naughty word backwards, or you personally might have called it whatever you want, but that's what I say. And so here is the ambiguous case. So if we have two angles and one side, it is a unique triangle. However, if we have two sides and one of the opposite angles, so it appears as though, oh, look, we're always going to have a side and an opposite angle, you know, and so our first thought is, oh, it's just going to work. So it can happen that no triangle exists, and so, you know, that's kind of when that third side hangs, kind of just hangs there and isn't long enough. One triangle, and there's more than one way to have one triangle. Like I'm thinking if it's an obtuse angle that we knew and we know those two sides, maybe, you know, there's only one triangle. Certainly if it's going to be a right triangle, oops, yeah, and we know those two and that one, it's gonna work. But if it's a right triangle, then it's like, if it turns out to be a right triangle, then we're going to have that 90-degree angle and kind of the SOHCAHTOA. And it can also turn out that it won't swing back to get that other leg. So this is just a couple things. Or we can have kind of the two distinct triangles, and this is where we kind of get that swing leg. So I'll just clone this little picture. So when we have this, then the leg either swings that way or it swings back the other way. And this swing leg, if I kind of put them both on one picture, you get a little, that green and red triangle would be an isosceles triangle. So there's a relationship there that we can find kind of the missing parts. So here is the information, and oh, evidently I drew a lot more. But here's the information for the ambiguous case. And so take a minute and really, you know, do look at this. And if now you want to draw these little triangles and label them, as you practice, you know, you'll get a little more intuitively acclimated to kind of what this situation is. But right now, just draw it down, draw it as you go. So the first 1, 2, 3, 4 cases is when A is an acute angle, and it might be that A is not long enough, or it might be that A and H are equal to each other. That's going to be a right triangle. That A is acute here, and there's one triangle. That A is acute, and that swing leg goes back and forth, so you get 2. If it's A is obtuse, you might have no triangle, and or you might have one triangle. And we'll talk about this, after this next test, but that H value that we're comparing things to is like what would be the altitude or making a right triangle, right? If it turns out to be a right triangle, so like that A equals H, oops, the second case there, that's what's happening. Because remember, the sine of A, SOHCAHTOA sine of A, is opposite over hypotenuse. So when you find B sine A, you're finding that leg that would be of a right triangle. So I'll leave you with that. You can pause it here to write that, or that is also in the book, and it'll be on the YOLA site as well.